Greetings and welcome, Internet friends. Mr. Waddy here, and you guys are already familiar with how to solve a system of equations that has two variables and two equations. Okay, and so that's something that you've done in the past, and you've learned to solve by graphing. You've learned to solve using substitution and elimination methods. And today we're going to talk about solving a system of three variables. And if I have three things that are unknown, I'm going to need three equations or clues about those unknowns in order to solve it. And so just like with two variables, I needed two equations. In one variable, I need one equation. In three variables, I'm going to need three equations in order to identify the value of x, y, and z that will make all three equations true simultaneously. Now, an equation with two variables represents a line. An equation with three variables actually represents a three-dimensional plane. And so think about that in terms of the geometry context that you might be familiar with. And so an example of a single solution of a system of three equations would be three separate planes or surfaces that are intersecting at a single point, and then that point would be your x, y, z coordinate. Okay, and don't worry, at least for this course, we won't be graphing these three-dimensional planes because it's quite difficult to do. Now, just like you were able to have infinitely many solutions with two variables whenever your two lines happen to be coincident, it can occur that you can have infinitely many solutions if, say, for instance, your planes intersect at a line. There are infinitely many points on that line. Theoretically, you could have two planes that are identical to one another, something to that effect as well. The equivalent of coincident lines, two lines that were the same line. And that would have many points and many solutions in common as well. And so it's possible to have infinitely many solutions, and we could describe those infinitely many solutions as being a type of expression in terms of one of the variables. And so we'll take a look at that as well. And then it's also possible that there are no solutions, and you could have, right, three parallel planes. That would make sense. You could have two parallel planes and one that intersects them in some sort of a transversal sense. And then you could also have planes that kind of make a triangular prism shape, where there's intersectionality between any two pairs, but there's no common intersection between all three of them. Okay, and so solving a system of equations algebraically, this is how you do it. Right, it's going to be similar to what we did in two variables. Rewrite the linear system in three variables as a system in two variables. Okay, and so we're going to use substitution or elimination to do that. So for substitution, I would solve one of the equations for one of its variables, and then I would substitute that expression into the other two, eliminating that original variable. We're going to focus on elimination method today, in which, right, I'll get opposite coefficients for one of the variables, and then by adding equations together, I can eliminate that variable. And if I can get it broken down into a system of two, well, I already know how to solve a system of two. And so that will be helpful for us, right? Solve the system for both, and then keep substituting back to find the remaining. If you ever obtain a false equation after your variables disappear, then the system has no solution. And if you have a true equation, an identity, where there's no variables, then there's infinitely many solutions. And so my little general strategy to summarize all this is eliminate the same variable twice, and you will get two equations with two variables, which is something we already know how to do. Okay, and so here's our first system. I'm going to get us in the practice of just labeling these, Here's equation A, B, and C. Each of these represent 3 different planes, and we're going to see, is there a point of commonality between them? Now, I'm thinking about elimination method, and so what I'm going to do is try to find opposite coefficients. And so presently there aren't any opposite coefficients, but I'm going to find the least common multiple between their coefficients. So for the x's, conveniently already lined up and on the same side of the equal sign, between 4, 2, and 6, 12 is the least common multiple. Between 2, 3, and 1, 6 is the least common multiple. And between 3, 5, and 4, is it 60? Yeah. And so I'm not going to be trying to get opposite coefficients for z here. No. And so what I'm going to do is I'm going to choose to eliminate y, because 6 was smaller than those other ones. And you could have done it the other way, but well, let's figure this out. And so this is a 2. What would I have to multiply it by to get 6? Well, I'd have to multiply it by 3. And so sometimes I haven't labeled the A, B, C yet, and so I would write multiply this whole equation by 3. That'll give me some 6y. Both sides, make sure you multiply by. Multiply this equation by 2. And multiply this equation by 6. Because 6 times -1 will give me -6y. Notice this one will be a positive 6y. Both of these will be negative 6y's. And so I'll be able to add them together and eliminate the variable. All right, and so here we go. I'm going to write, what do I get when I do 3 times equation A? Well, 3 times 4x is 12x plus 6y plus 9z equals 3 times 12 is 36. Don't forget to multiply the other side of the equation as well. Then I've got 2 times equation B will give me 4x minus 6y plus 10z equals -14. And what did I get when I did 6 times Charlie? I've got 36x minus 6y plus 24z equals -18. All right, and so obviously with all of this arithmetic and algebra, a single mistake is going to be a challenge. It'll bleed through the whole problem, so careful with your arithmetic. And so now that I have opposite coefficients, right, I'm going to start adding these equations together. And so the first one I'll have is 3a plus 2b. And you are welcome, by the way, to like relabel this instead of calling this 3a. You could have called this D, E, and F. That's fine. Right? I'm just trying to find a way to communicate where these lines of work are coming from. So let's add 3a and 2b. So 12x plus 4x is 16x. The y's cancel out. I've got plus 19z equals... and 36 and -14, I believe, is 22. And then over here, I'll do 3a plus 6c. And I'm adding these because the y's are going to cancel out. I'm eliminating the same variable twice. Okay, I don't want to like eliminate one variable here and then another variable there, because then I'll have 2 equations, yes, but this would have x's and y's, and this would have y's and z's, and there wouldn't be a commonality for me to solve. So let's do, get rid of that. 12x and 36x is 48x. The y's cancel out. 9z and 24z is plus 33z. And what am I adding here? A and C, yeah. 36 minus 18, I believe, is 18. Oh boy. Now, now I've got a problem like I would have had in our Algebra 1 textbook from Chapter 5. I've got 2 variables, x's and z's, and 2 equations. And so, tell you what, I'll relabel these. I'm going to label this D and E. And let's figure out how to solve these. And so between 16x and 48x, 48 is a least common multiple. Between 19 and 33, I'm grabbing my calculator for this one. 19 times 33 is 627. I'm not going to use that one. Nope. All right, and so I'm going to go for this. So this one's already got a 48. I want this to be a negative 48 to cancel with it. And so I'm going to multiply this equation by negative 3. Right? I'll tell you what, I'll write it here. And so I'll have negative 3d is equal to negative, I'll swap my colors again, negative 48x. Negative 3 times 19. I don't trust myself. I think it's 57. Yep. And it's a negative 57z equals, and negative 3 times 22 is negative 66. Okay, and so you can see where it'd be easy for me to, lose track of my work, and that's why I'm recommending some way of labeling your steps. Okay, so I want to combine negative 3d plus e, and that is going to eliminate these x's. And so those get added together, they cancel out. 33 minus 57, I've got negative 24z equals 18, and negative 66 is negative 48. All right. Oh, wow, man. Whew, crazy sauce. Am I right? Now, notice I've got one equation and one variable, and that's when I can use like my chapter 1 algebra skills to solve. I'm just going to solve using inverse operations. So z is being multiplied by negative 24, so let's divide both sides by negative 24, and I get z equals positive 2. And so I solved for one of these equations. And, well, I've solved for one of these variables. Now I've got to figure out what are the other variables. What are x and y? And so I can take this z, and I could technically plug 2 in for z here, or here, or here, or here, or here. But I'm going to want to plug it into a spot that only has one other variable. And so preferably one of these, because both of these have z's, and then they have x's, and that'll allow me to solve for x. And so I'm going to plug this in here. And so I'm going to plug, tell you what, oh dear, I'm going to use function notation for this. Kind of. So I'm calling this equation D. And so I'm going to say D of, oh dear. What's a good way for me to write that? I was going to say D parentheses Z equals 2. No, I'm just going to do it. We're going to do it. Roll it from here. So 16x plus 19, and instead of Z, I'm going to plug in 2. And so what that allows me to do is solve for x. So 16x plus 38. Subtract 38 from both sides. I get 16x equals, I don't trust myself, guys. This is way too important, right? Like one error, oh boy. Divide both sides by 16, and I get x equals -1. And so now I've got 2 of my variables solved for. And so now to solve for y, these equations all have a version of y. These equations all had a version of y in them. These ones had smaller coefficients, and this one actually is the easiest one to solve for y. So I'm going to plug this in for z, and I'm going to plug in this for x, and solve for y. So 6 times the x minus y plus 4 times the z equals -3. And so I was plugging in -1 for x, I'm plugging in 2 for z. So I get -6 minus y plus 8 equals -3. Combine like terms, the opposite of y plus 2 equals -3. And yeah, these take up quite a bit of space. So I would account for about a page of space per problem. And then y is going to equal +5. And so my solution is a -1, 5, and 2. Right? And I put that ordered triple in the order of x, y, z. Alphabetic order. How convenient. All right. And so there's one problem. And yeah, it takes a little while. Right? Going to take it slow. We're going to take our time with plugging in, calculator if need be. And yeah, we're able to solve for this equation. Excellent, excellent, excellent. Let's see. Here's a situation in which there's going to be no solution. So let's figure out coefficients. So here the x's, the least common multiple between 1, 5, and 4 is 20. Between 1, 5, and 1 is 5. Between 1, 5, and 3 is 15. So yeah, I'm going to go for y's again. And so yeah, this is right, my a, b, and c. I'm going to have to multiply this top equation by, tell you what, I'm going to do -5. I'm going to keep this one the positive. And I'm going to multiply this one by -5. And I don't have to do anything to this one. And so let's figure out what's -5 times equation A. And I would have -5x minus 5y minus 5z equals -10. And then I'll figure out -5 Charlie. -5c is going to equal -20x, right? Minus 5y and plus 15z equals +30. And now I'm going to add equation B, this one, to these two things to eliminate those y's. So I'll have -5a plus b. And this is where, so I'm adding this and this. And with all of these lines, it's easy to accidentally add the wrong pieces together. So I'm adding this and this, this and this, right? This and this, etc. So take your time, take your time. 5x and -5x, oh, those cancel out. 5y and -5y, those cancel out. 5z and -5z, well, those canceled out. And then I get 3 and -10 is -7. And so that's false. And there was no variables, right? And so I was left with a false statement. And so therefore this equation has no solution. Okay. And so I don't even have to figure out combining this and this, because I ended up with a situation where all my variables disappeared and I had a false statement. Okay. Let's take a look at example 3. And I think that's all I'll end up doing for this video. And we're spending like 3 days on this unit, and then we're going to apply this to a couple other units that we've been in already. It'll be good. It'll be good. So between 1, 1, and 5, the least common multiple is 5. Between 1, 1, and 5, the least common multiple is 5. Between 1, 1, and 1, oh, let's use those z's. I don't even have to multiply, right? Because these already have opposite coefficients. So I'm going to do a plus b. Wow, what do you know? And so if I take a and b, x and x is 2x. -y and -y is -2y. The z's cancel out, and I get -3 and -3 is -6. Now, I can't add a and c because those won't get eliminated. But I can add b and c, and right, then I'll eliminate one of those. And so I'll do b plus c. X and 5x is 6x. negative y, negative 5y is negative 6y. The z's cancel out as we were expecting. And negative 3 and negative 15 is negative 8. And so now I have a system of two with two variables, right? Two equations, two variables, and they're the same pair of variables, right? X's and Y's. And so now let's eliminate again. Between 2 and 6, I could have a least common multiple of 6. Same thing here. And so I'm going to take this equation. Tell you what, I'll call this equation D and E. And so I'm going to multiply equation D by what to get the opposite of the 6x? Well, negative 3. So negative 3D would give me negative 6x plus, all right, 6y. Yep. And I got to make sure I'm looking at the right line here. Negative 3 times negative 6 is positive 18. Wait. Oh, guys, I had a typo right here. I was beginning to get suspicious when I did negative 3 and negative 15. That's negative 18. Boom. Okay. So now I can add negative 3D plus E, these two equations, and notice cancel, cancel, cancel. I get 0 equals 0, which is true. Therefore, this has infinitely many solutions. Now, one of the things we can do, because I have infinitely many solutions, is I'm going to try to write an equation or an answer, a way to describe that answer where everything is in terms of one of my variables. Okay? So I'm just going to say, let the solutions be in the forms of, right, x. And so I know that x is going to equal whatever x is, and there's multiple, there's infinitely many solutions. But let's solve the second equation for y, and then the third equation. We're going to try to get everything in terms of x, is what we're going to try to do. Now, actually, do I want to solve? Yeah, which one should I solve for? I think actually I want to solve for one of these, because I could get one of these in terms of y. So I'm doing substitution style here. So let's see. So I'm going to take E or D. Yeah, I'll take D. So I'm going to solve D for y. And so I'll have 2x minus 2y equals negative 6. I'll bring the x to the other side. And so what this is allowing me to do is to rewrite y in terms of x's. Divide everybody by negative 2. And I'd get y equals x plus 3. And so my solution, the y, is all possible y's that are of the form x plus 3. So 3 more than whatever my x coordinate was. And now in order to solve for the z, I'm going to take this y and I'll plug it in. I need an equation with a z. Yeah, it looks like this or this are pretty easy. Let's actually plug it into the top one. And so I'm going to plug it in for this because the z was positive. So I'm going to have x negative y z. So I'll have x minus y plus z equals negative 3. So I'm substituting this in for y in equation A. And so notice what this is going to do, let's see, is I'll be able to solve for z in terms of x. So distribute x minus 3 plus z equals negative 3. I can then, what do you know? X minus x, those just cancel out. And then I could add 3 to both sides. And I'd get z equals 0. And so my solution are all possible, right? All combinations of points in which the x is whatever x is, the y is x plus 3, and z is 0. And so that last part is probably a little bit weird, but what you're trying to do is write all of your your answers, your 3 points, coordinates rather. I guess they're not coordinates, they're triples. Because coordinate would be 2. Triple is for 3. You're going to try to write your ordered triple all in terms of a single variable. In this case, the z didn't have any x's. It just was always the same. And so there's infinitely many solutions that, as long as they meet this criteria, they fit that form. That's one way that I can describe it. Tell you what, I'm going to take a quick setup tour of these. Many of you could probably move on. The video has been long enough. But between here, if I was doing elimination, I could go for 3s. These ones already have the 2s, and then here I would have 4s. So what I would end up doing would have multiplied. Oh, I would have just used these. Yeah, I would have done a plus b and then a plus c to eliminate the y's, right? And then go from there. Let's see. For this one, this is the monitoring progress questions, by the way. Between 1, 4, and 3, 12 is the least common multiple. Between 1, 4, and 2, it's 8. And between 1, 4, and 1, it's 4. So I would have gone for opposite z's. To get this to be a negative 4z, I would have had to do 4 times a. And I would have had to do 4 times c in order to get all 4s right for those, and then I would have gone from there. I just want to help you guys out on the beginning step for these ones if you want to practice them. Between 1, 1, and 2, the least common multiple is 2. Between 1, 1, and 1, oh, that's 1. That's golden right there. And between 1, 1, and 2, the least common multiple is 2. So I would go for opposite y's because that's the easier number. You don't have to do it. I'm just trying to keep numbers small. And so I already have opposites for all of them. And so I would have done a plus b, and the y and the negative y would cancel out. And then I would have done probably b and c together, right? To get negative y and y cancel out. And then I would have had a system of 2, and I would have solved the same thing. All right, well, thank you for watching, Internet friends. Have a great day.